I have a video on factoring polynomials, finding their rational, irrational, and imaginary roots. We talked in our last video about how I can take this expression, this polynomial, and using synthetic division, I can check to see if a number is a root. So say I pick the number -4. And I'm picking this because I know it actually is a root, but here's how we can check. I drop down the 2 and I multiply. -4 times 2 is -8, and I add 5 minus 8 is -3, and I multiply. -4 times -3 is 12, and I add. -11 plus 12 is 1. Multiply, add. Since this came out to 0, this tells me that f of -4 equals 0, which means that x equals -4 is a root, or a 0, and that x plus 4 is a factor. Well, the fact that x plus 4 is a factor is nice. That means I could actually take this polynomial and factor it into x plus 4, and whatever these numbers left behind were is the remainder of the expression. So I factored out the x plus 4. Well, now I can do it again. Suppose that I know that 1 is a root. I take these numbers now, 2, -3, and 1, and I go again. I can drop down 2, and I multiply, and I add, and I multiply, and I add. So this means that 1 is a root. So x minus 1 is a factor. And now I have from before, the x plus 4 is one of my factors. The x minus 1 is another of my factors. And all the stuff left behind here is my third factor. So my solutions are really going to be -4, 1, and 1/2. These are all my roots. Well, the trick here is I knew in advance what these values were. I knew that the roots were already -4 and 1, but the question is, how can you know that? How can you find those in advance? Otherwise, it doesn't really help you at all. Well, the really cool little trick is called the rational root theorem. Here's what this says. If I think of all the factors of, with orange here, all the factors of 4 and all the factors of 2, and I divide them. So I take the y-intercept, and this is going to be the value p that we work with, and the x-intercept, I'm sorry, not the x-intercept, the leading coefficient, this is the value q that we work with. Well, the factors of p are plus or minus 1, 2, and 4. The factors of q are plus or minus 1 and 2. What this rational root theorem says is that all of the rational roots, meaning all the roots that can be written as a whole number or as a fraction of 2 whole numbers, 2 integers, are going to be some combination of these. So it could be like 4 over 2, it could be -4 over 2, or it could be 2 over 1, or -2 over 1, or it could even be like 1 over 2, or -1 over 2. But basically in this case, the only options for real roots are plus or minus 2, plus or minus 1/2, and also I could do like plus or minus 1. Those are the only options for real roots. And then what you do is you just check them. Oh, I guess I could also do plus or minus 4, because that was clearly one of them. Just do 4 over 1. 4 over 1 is plus or minus 4. You take these possibilities, and you plug them in synthetically, and you see if you get out a 0. So, you know, since I knew in advance that -4 and 1 were roots, I plugged them in and I got out zeros. But in the next problem, I don't know what the roots are here. What I can do, though, is say my p-value is 6, so it could be plus or minus 1, 2, 3, and 6. So those are all the factors of p. My q-value is just 1, so it could be plus or minus 1. So the possible roots are 6 over 1, 3 over 1, 2 over 1, and 1 over 1. Really, it's just 6, 3, 2, and 1, and these could be positive or negative. These are all the possible rational roots. By rational, it kind of just means clean, not really ugly decimals that go on and on forever without ever repeating. So I'm going to pick one. I'm going to try it. 6 seems a little bit too big. Be kind of smart about this. If I'm going to plug a 6 in for x, this is going to become 6 to the 3rd, and it's going to be way too big to make this work. My guess is it's something like 1 or -1 or 2 or -2. I'm going to try 2. So if 2 is a factor, I have 1x to the third, 0x squared. I'm going to have to account for all of those terms. I need to have that 0 there. If I plug in a 2, I go 1, 2, 2, 4, -3, -6, 0. Ha! I didn't even know that was going to work, but it did, so I'm happy. I got out a 0. This means x minus 2 is a factor. What's going to be left is, since this was x to the third, this is going to go 1x squared plus 2x minus 3. Now here's what's really nice. I know these are still my possibilities for real factors, but now I can play the P and Q game with these numbers. Here the only options are actually going to be plus or minus 3. Because my Q value is -3, so it's just plus or minus 3. My P value is, I got those backwards anyways, P is -3, Q is 1. It doesn't really matter, -3 over 1. So I'm going to try, do I think 3 works or -3 works? I think it's going to be -3. So I'm going to plug in -3 and see what happens. So I'm going to do -3 into 1, 2, -3. 1, -3, I add these up, I get -1, I multiply, I get 3, I add these up and I get 0. Ha, I got that one right also. So this means that x plus 3 is a factor. So far I've had factors of x plus 3 and x minus 2. And this last one is x minus 1. This becomes 1x minus 1. And those are the 3 factors of my original polynomial way up here. And that's how I could solve it. It has solutions, has roots at -3, 2, and 1. So that P and Q trick is a really quick and easy way to find possible values, and then just be kind of smart about what you plugged in. I looked and realized that 6 was way too big to try and plug in, so I tried 2 first, because 2 seemed reasonable. The fact that it was +2 and not -2 was nice, because it could have been a -2. And there you go. So this one's going to have imaginary roots. If I try and play the P and Q game here, it gets really annoying, because if this is my P value, and it could be -1, 2, 4, 5, 10, or 20, plus or minus, and my Q value is 1, well, now there's 1, 2, 3, 4, 5, 6 things that I can check. And if my Q value wasn't 1, say the Q value is 4, well, now there's going to be like 18 or 20 possibilities, lots of possibilities. It could be 5 over 4, or 2 over 4, or 10 over 2, or all kinds of possibilities. So as these get really big, it's kind of a pain to play the P and Q game. Luckily, we've got a machine that basically guesses and checks at an infinite speed for us. If I go to my grapher and I plug in the original equation that doesn't have the 4 on it, but I plug in 1x to the third minus 5x squared plus 4x minus 20, and I graph it. Well, right now, if the window's not really great, I can see there's some kind of stuff happening down here. There's not anything happening over here, so I'm going to make my y values go up and down further. I'm going to go from -50 to 50, and I'll count by tens. That's what that scale means, count by tens. Now I've got a pretty good idea of how that graph looks. It is only crossing the x-axis one time. That means this only has one real root. There's going to be 2 imaginary roots. Remember how whatever your degree is, that's how many solutions there are? This will have 1 real root and 2 imaginary roots. The nice thing about imaginary roots is they always come in pairs. You can never have just one. It's always 2 or 4 or 6. They always come in pairs. When you find one, you find the other, and I'll show what I mean by that. I can look at this graph and get a pretty good idea that this root is at 1, 2, 3, 4, 5. That the value of x equals 5 is probably a root. So we'll check to make sure. I'm going to plug a 5 into this box up here in the corner. I go 1, -5, 4, -20. Well, I drop down the 1, and I multiply, and I add, and I multiply, and I add, and I multiply, and I add. Since I got out 0, this means that this is a root. So one of my factors is x minus 5, and what's left is x squared plus 4. Well, if you think about x squared plus 4, think about the graph and how that graph looks. The graph of x squared plus 4 looks like this. This isn't going to have any more roots. There's no more real solutions here. So there's nothing else that I could plug in to solve. But I know that I want this to come out to 0. So what I can do is take x squared plus 4 equals 0 and solve this. And one way you can solve these things is if you have the quadratic formula. In this case, the quadratic formula isn't really necessary. I can just, since there's only just one x, I can just solve this like regular, subtract an x squared, or subtract a 4 from both sides, and take a square root, and I get plus or minus 2i. Those are my other two roots. Since those are my roots, here's how this factors. X minus 5, x plus 2i, x minus 2i. I have factored the equation. It has roots at 5 or plus or minus 2i. So basically, you take your synthetic division process and you do it as far as you can. Had I had more options, had this been like x to the 5th, I probably could have done the synthetic process 3 more times to get more of these real bubbles. But then I got down to something that can't factor, and I know it can't be solved because I understand how these quadratics work. I also looked at the graph in advance. And in advance, I could tell that there were going to be imaginary solutions. That's what this stuff is here. This stuff here is the imaginary solutions. So on my calculator, I found where the real solution was, did synthetic division, and then with what was left, the stuff over here, the stuff that was left, that's when I did the quadratic formula, or I solved. Last example, this one's going to have irrational solutions, meaning they're ugly. They're going to be real numbers. They're not whole numbers, but they're real numbers, but they're ugly. So I'm going to graph x to the 3rd minus 5x squared minus 6x plus 30. And there's that graph. Now one of these is really clean. 1, 2, 3, 4, 5. Again, this has a nice clean root at x equals 5. So let's do this synthetic work and see what else I get. 1, negative 5, negative 6, 30. So I'm left with x squared minus 6. So I have x minus 5 as one of my factors, and this gives me x squared minus 6. Well, this one is going to give me an actual real solution. If I take x squared minus 6 and set it equal to 0, this can be solved for real. I get x squared equals 6, which means that x equals plus or minus the square root of 6. So my factors are going to be x minus 5, x plus root 6, and x minus root 6. And the nice thing is you can check these on your calculator because these roots actually exist. Let me find this root right here. To do that, I do second trace, which pulls up my calculate menu. I want to find a 0. I take this little spider and make sure it's on the left side of that intersection. So I can actually just hit enter anywhere over here. Press enter. Then I scroll to the right, all the way over to the right side of the intersection. Not too far, but far enough. Press enter. It says guess, skip that, press enter one more time. This says 2.45 basically. So let's find the square root of 6. 2.45. So these match. This was correct. Here's your plus or minus. Irrational roots. Irrational means numbers that are square roots that can't simplify, basically. So like square root of 4 is not irrational, but square root of 5 is irrational because it can't simplify. Irrational roots always come in pairs, just like the imaginary roots did. Irrational roots and imaginary roots always come in pairs, and that's pretty convenient. So to recap what just happened, sorry, not yet. This graph here has 1, 2, 3, 4, 5 real roots. All of it's real. Some of them might not be clean, like this one looks like it's a whole number, but this one here and this one here is probably going to be irrational just because of where the decimals would be and how ugly they look. This is just some stupid graph I made up, but that's all real. This graph has a few real and a few complex ones. It has real roots here, here, and here, but it's going to have complex roots here and here, and I think that's all. I think this will have 2 complex roots. When you have curves that don't cross the x-axis, that's when you know you're going to have complex roots. when you have curves that don't cross the x-axis. It's possible to have all complex. This has no real roots. It's a quadratic that doesn't cross the x-axis. No real roots and 2 complex roots. So you can tell by looking at a graph that way. So to recap, rational roots are always found at p over q, where p is the factors of the y-intercept and q is the factors of the leading coefficient. Irrational and complex roots always come in pairs to the plus or minus. And synthetic substitution allows you to factor a polynomial into intercept form, which is ideal for solving and graphing. Thank you. Hope you have a wonderful day.